Hey, howdy everyone. This is Michael Perch. I'm an associate professor at the University of Texas at Austin, and it's my pleasure right now to go ahead and cover the very last lecture of my Subsurface Machine Learning course. So this is the concluding lectures for the course. If you're interested, there are, I think it's quite a few videos, lecture videos, probably around 30 or so, available all within this playlist, and it covers everything from fundamental probability, data analytics, machine learning, all about how do we build machine learning models with a focus and context around the subsurface. All right, so let's finish off. This is fun. I always like recording these lectures. The very conclusion, what's the motivation here? What do we want to do? Well, this lecture is everything you need to remember to succeed in the fourth paradigm of scientific discovery as an engineer or scientist. And so what am I talking about? Of course, historically speaking, human development and how we learn from the natural system around us. Well, experiments have been going on for a long time. Very, very interesting things were being done even back well before, thousands of years ago, 1600 BC, there's been, evidence of interesting experiments being conducted. Of course, around the 1600s, we start to think about more theoretical science. How do we develop analytical expressions, formulas, equations to describe fundamental laws of nature around us? Super epic, super cool. And then the third paradigm, of course, with the advent of computational power, dealing with complicated heterogeneous systems and realizing there wasn't analytical closed form solutions, but we could model the system. If we had a powerful enough computer, we could formulate a model that would be able to capture that. And I think about, the development of aircraft right in the computer. Imagine that. Recent developments of aircraft where they weren't even using models within a wind tunnel, but they were actually able to model the behavior, all those control surfaces and so forth, completely in the computer. Fascinating. Well, of course, now we're in this fourth paradigm, where the thinking is that sometimes we have systems that are so complicated that we don't really have mathematical models for them, but we have enough data or observations, and we approach it from a data-driven scientific discovery approach, trying to detect patterns, anomalies in big data, artificial intelligence, machine learning types of methodologies, and so forth. So, welcome to the fourth paradigm. If nobody else has said that to you, I would love to have the chance to say that to you. Now, at the same time, and this is something I've said recently, and I'll say it again, is remember, just because we got into the third paradigm with computational resources, we didn't throw empirical science away. We didn't throw theoretical science away. We need to work with all of the paradigms in order to understand the natural world around us. I'll hit that again and again. Okay, so that's the motivation. What are we going to do as engineers and scientists, geoscientists and so forth, to be able to succeed in the presence of the fourth paradigm? And so what is the role of machine learning? And so many of us do this. If you want to learn about something, you look it up on Google. One of the first things to show up, thank you very much, Wikipedia, great resource. And so machine learning, the machine learning article in Wikipedia, if you read through it, it's quite revealing as far as the role of machine learning. And so let me just quote from it, is the study of algorithms and mathematical models. Now notice the deliberate use of plural. It's a toolkit. It's not just one model. It's many, many models that you can work with that computer systems use to progressively improve their performance on a specific task. Learning. It's a methodology that will learn and improve its performance. Machine learning algorithms build a mathematical model of sample data known as training data. Learning with data, working with training from data, in order to make predictions or decisions without being explicitly programmed to perform the task. It's a general methodology. You make a tool, it's able to perform many different tasks. It wasn't specifically designed for that task. Now, what's interesting is many people, when they read through Wikipedia articles, probably stop in the first couple of paragraphs. They may not get right to the end. if you continue to read through the article, near the end you'll see the following statement. Where it is infeasible to develop an algorithm or of specific instructions for performing the task. So what's that tell us there? It's not a panacea. It's not a solution to all. In other words, and I'll say this again, when you understand the engineering, the scientific principles, use that knowledge. Don't go just data-driven. In fact, that can be very dangerous. All right, so I'll comment a little bit more on that. Where am I coming from? What am I thinking? Well, I have a bias, and this is my bias, and I revealed it pretty clearly. I was asked to be on a panel for PricewaterhouseCoopers just back in April last year. And so I was on this panel with 3 other experts. Well, we had a convener there, a moderator, and other experts, the other 2 experts there. And we were asked to stand in front of or sit in front of a group of vice presidents, executives from subsurface development, energy type companies. And they wanted to know what we thought about the digitalization revolution going on right now. And so here's my bias. This is the message I shared with those executives. I said, there are opportunities to do more with our data. In fact, what I would say is that probably the P10, which would be the low case result from all of this, is we just do a better job with our data and we treat our data better with more respect. We do a better job of data curation and so forth. There are opportunities to teach data analytics and statistical and machine learning methods to engineers and geoscientists to improve their capabilities. Clearly, that's a great opportunity. And I applaud all the companies. I taught in about 20 companies last year, I think, something like that. And I see great efforts going on to build new capabilities for their people. But geoscience and engineering knowledge, expertise remains core to our business. Human innovation is at the root of any new opportunities in our business. We really do need human innovation. Every time there's been new value, it was creativity. And that does come from the professionals who have domain expertise. It drives it all. Now, also, we need to demystify machine learning as a community. Remember, when we are doing machine learning, we're setting up a mathematical model. The model has predictors or independent variables or features. Those are inputs. It has response dependent variables or features, which are outputs. And everything we do in machine learning is all about estimating this model really for 2 purposes: inference and prediction. Learning about the system or getting the very best forecast of the next possible result. That's what everything is about here. In fact, I had a student come into my office and they had this great idea. They had all this stuff and this data they were working with. And I asked them, I said, what's the inputs? What's the outputs? What's the goal here? What are you trying to do? And it was interesting. They just kept talking about all this exciting data and just really kind of just so enthusiastic. I had to ask about 3 times before they sat back and they were, I don't know. And I said, well, this is what it is. It's a model. It's simply just a model. Let's demystify it. Let's realize that it's got inputs, outputs, and let's map fit for purpose the goals of the project. Data curation, data preparation is critical too. Remember that. 80% of any spatial subsurface modeling project I've been on has been data preparation and interpretation. Often it's more than 80%, to be honest. We continue to face a lot of challenges in data curation, the large volumes of data. We got big data. Oh, you bet we got big data. We've been big data long before tech knew what big data was. Large volumes of metadata that we don't necessarily do a great job with. Geez, so many decisions around interpretation, the versions of the data we work with. There's a lot of data about data, the metadata. A variety of data, scale, collection, interpretation, and oh boy, transmission controls and security. I've been on projects where the data couldn't leave the country. You know, it's very, very, very challenging. Clean databases are the prerequisite for all data analytics and machine learning. we must start with this foundation. Build a good data table to get started with. Garbage in, garbage out remains in effect even with these really great data analytics and machine learning methodologies that we use now. Now also remember this. We got to build from a foundation of probability and statistics. If you don't have that foundation, you indeed are building on a very sandy foundation. Consider the naive Bayes classifier that we discussed in class. This classifier, the whole prediction model, is built directly from Bayes' theorem with the assumption of conditional independence. And we covered that, we discussed it. But in order to use that model effectively, to work with that model, we should really understand the concept of Bayesian updating, Bayes' theorem, Bayes statistics. All right. Also, there are many times that we can get the job done using very simple methods like conditional joints and marginal, statistics, distributions, probabilities to learn from the data. Here's an example right here where we want to go from acoustic impedance, inverted from available seismic information, to porosity, a petrophysical measure that we're able to then be able to use for the purpose of predicting subsurface behavior, fluid flow, and so forth. If we have enough data, we can just map out and work with conditional joints, distributions, probabilities, and we're able to have very powerful, flexible prediction methods. I've worked on projects before where we had enough data. It was a low enough dimensional problem where we could actually work this out. Remember, this is all derived from fundamental probability and statistics. Always remember that energy is different, or many of the subsurface fields, not even just energy. We're talking about water and mining and geothermal or anything to deal with the subsurface is going to be dramatically different than many of the other types of problems that people use data analytics and machine learning for. And so we need new solutions. We deal with fundamentally sparse, uncertain data sets. We have very complicated, heterogeneous, open Earth systems. They always surprise us. And there's a high degree of necessary geoscience, other branches of science, engineering, interpretation, and physics cooked into all of our workflows. We need that. We can't just be data driven. We have expensive, high-value decisions that must be supported. Just consider the cost of subsurface development in any type of field of endeavor. It's incredible the costs that are involved in working with the subsurface. Now, compare and contrast this to other areas in which machine learning are being used. And so a good example is a recommender system or engine. And so popular ones include Amazon. When you go on Amazon, it looks up your history of viewing and purchases. It makes recommendations for what product you might want to look at next. Okay, now let's think about that. That's incredible. So how about Spotify? And so, for example, this is my Spotify account from the Spotify recommender system on my account back from last summer, 2019. And I'm Canadian. I listen to a lot of Canadian music all the time. I'm tragically hip. Gord Downey, we still miss you. And so I think there's a lot of great Canadian music. And so I have Spotify playing while I work. I like to have a little light music while I work on campus. And once in a while, Nickelback will come on. Well, because I'm Canadian, I listen to a lot of Canadian music. And Nickelback comes on, I'll start bobbing my head, tapping my foot. Hey, this is kind of catchy. And then I remember, this is Nickelback. I don't like Nickelback. In fact, I don't think any Canadians still like Nickelback anymore. Sorry, Nickelback. But so what's the cost of that? Because that's completely wrong. I promise you, I don't like Nickelback. That recommender engine got the recommendation completely wrong. It's wrong. It's completely wrong. But what was the cost of being wrong? That cost is literally zero, because all that's going to happen is I'm going to fast forward the song. I'll keep going. I don't cancel my account. I don't start some protest and get everyone to cancel their accounts. There's no consequence at all. There's really no value or risk associated with those decisions of recommender engine in this case. It can afford to be wrong all of the time. This is so different than what we do in working with the subsurface and our complicated spatial engineering and scientific problems. We have to be a critical user, consumer, and at times developer of this technology, workflows and so forth that we share with others, to recognize that we are very different than many fields that use this technology. What I would suggest is because of that, many of the methodologies are not ready right off the shelf for use. We need to make changes in the workflows, I would suggest. All right, remember this concept of the model variance bias trade-off. So remember that and realize there's motivation to not jump to high complexity models. I've seen that over and over again. I went and taught in an organization and I said, okay, today I haven't taught you before. Let's start from basics. Let's start from probability, statistics, data analytics, and let's work up. And they said, no, we're experts here. We all do convolutional neural nets in our daily jobs. We don't want to do that. I said, okay, well, let's just give me an hour. Everyone got excited talking about fundamental, frequentist, Bayesian probabilities, how they could be used. They started to show practical workflows. We started from the, and we were building a foundation. So remember, there's an analogy there that even the models themselves benefit from simplicity. Look at the expected test mean squared error formulation, the model variance and bias trade-off. When you look at the behavior, model variance, complicated models will tend to be much more sensitive to the actual training data set. And so as model complexity increases, we're going to lose because of model variance. It becomes our enemy. Model bias is this concept of a too simple a model is unable to capture the natural setting. And as we increase model complexity, we'll gain, we'll do better. And irreducible error will be constant because it's just a function of the data and what's missing from the data. Now remember, what do we learn from all of this? First of all, what we learn is that we can't replace data with more modeling. That irreducible error is not being attacked by the modeling methodology. We only get at it when we have better data to work with. In many projects, that is the most important. Also, often, simpler models can outperform complicated models because they reduce model variance, and I didn't write it here. We actually have better model interpretability, which is critical to us in the subsurface when we work with simple models. This can really help us out. Okay, so let's talk a little bit more about interpretability. It is critical. In fact, from my experience in working with large projects in the subsurface, I can't imagine making a funding decision for subsurface development using a methodology that's not understood by the experts in the room, the scientists, the geoscientists, the engineers. I don't think we'd be able to do that. All right, so we need to develop methods and workflows that provide useful diagnostics so we can understand them. Why? Because interpretability may be in fact very low from the model we're using. Very complicated models have low interpretability often. Application may become routine and trusted when we're working with a preferred workflow. Now this is very interesting. Anybody ever worked with a standard workflow within an organization? Have you ever tried to change it or not use it and then present your results? You've broken a social contract effectively. Everyone in the room will be uncomfortable. They'll be, what's happening here? There's some explaining to do. Now imagine if you have low interpretability and you have a workflow that becomes a trusted authority. The machine's trusted, it becomes an authority, but it can't be questioned. That right there is very challenging. Okay, so Ribeiro and all, they have this paper back from 2016. And it's a really fun read. There's a link for it right there. You can get it online on an archive. Post-print. And it's a very simple example. They did it to demonstrate this point. They took pictures of dogs and wolves. And when they did that, they built a logistic classifier that came out with a probability of dog or wolf based just on the image. And when they did that, this picture came back as high probability wolf. This is wolf. And so they went back and they looked at the machine and they said, okay, tell us which pixels in the image gave you the sense of high probability of wolf. And when they did that, it was these pixels right here. In other words, it was the fact that the dog was standing in snow made it look like a wolf. And that actually makes a lot of sense. I'm Canadian, I get it. A lot of wolf pictures in northern Canada and the dark Arctic. They're standing in the snow, they're howling. They're always in the snow. And so this dog just being the wolf. And the problem here is that if we had not interrogated the machine, we'd have no idea how that choice was made. And if the choice was very complicated and we could not diagnose it, we couldn't QC it so readily, or we failed to QC it, we would just be wrong. The system would be wrong. Peter Haas in his TED Talk used this example and talked about his fear of AI not being Skynet and taking over the world or something, just this idea of trusted authorities and systems that just get it wrong. His quote, I really like it. He says, even developers that work with this stuff have no idea what it's doing. Some of the systems are very complicated. I also like another quote from his talk. These systems do not fail gracefully. When they fail, they really, really fail. Like this dog and wolves example right here. I love that. Very powerful. I'd also say find novel methods to communicate. Don't baffle your audience when you use data analytics and machine learning. If the work can't be understood, it's not going to be used. In fact, I remember when I was working in our industry for quite a while, there was a great scientist, geoscientist that I worked with, Bruce Power, he said, Michael, there's many very complicated ways we can tell ourselves what we already know. In other words, don't build up this very complicated workflow, fail to communicate the workflow in a practical manner, so that if everyone's baffled by it, they're not going to be happy or excited to use it. Remember, the best way to improve your career, to promote yourself, is to share your knowledge and replace yourself, empower others, teach others. You're carrying this data-driven, data analytics, machine learning light to all the professionals around you. Empower them, teach them what you're doing. Here's a simple example right here. Predicting a subsurface performance as a function of a petrophysical and more of a geomechanical feature. And here's the model. It's a classification model where we have different flow rates, low flow coming from the subsurface from wells, high flow coming from the subsurface. Here's the training data. The training data, black points were the high flow rates, white points were the low flow rates, and you can see the decision boundary from the model. The model can be perfectly interrogated. We can see the performance. We can see the degree of flexibility. This was naive Bayes, so we could even talk about the prior that we put into it and what impact it had on the resulting model. This greatly simplifies the idea of machine learning to decision boundaries mapping in the predictor feature space. We can communicate that rather than baffle our audience. Now, in this course, you were forced to code, and there were some students who really hadn't done much coding before, and I saw and I respected the effort that you made to learn to code. Stay on this journey. This is a powerful journey. I love it. I spent decades doing C++, Fortran, full stack development, developing large applications and subsurface modeling. I really did enjoy coding, and I've never regretted the fact that I've continued to learn how to code. A few years ago, picked up Python, started to work in Python, and I've enjoyed that very much. Be flexible, keep learning. If you're not motivated enough to learn to code, here's some reasons right here that I could share with you. Reasons all geoscientists and engineers should learn to code. Well, first and foremost, transparency. No compiler accepts hand waving. You don't get to just wave your hands around and try to explain something. Coding forces you to expose your logic for everyone in the world to be able to interrogate it. Guess what? It opens you up, and you're going to learn from that experience. It's better than being a genius in your own mind, right? Reproducibility. You run it, get an answer handed over, they run it, get the same answer. That's the main concept. One of the main concepts of the scientific approach. That's great. Quantification. Programs need numbers to run. It's going to force you to quantify more. I personally am on a bit of a journey, a belief I have that more and more can be quantified within the subsurface, and it's always very powerful. It's a new lens to see the world every time we quantify something new. We feed the programs, discover new ways to look at the world through quantification. Open source development. Oh my gosh, leverage the world of brilliance. Check out a package, grab a snippet of code, Be amazed with what great minds are so kindly sharing, freely sharing with each other. I was building a subsurface model and I needed a methodology to build a trend model with sparse data. And the best package I found was AstroPy. It's an astrophysics type of package for Python, and I was using it for sparse data convolution so I could build some really nice trend models. So awesome. Break down barriers. If you are involved in the coding, you're not just coming up with a workflow or idea and throwing it over the fence to the developers to build it out. Sit at the table with the developers and share more of your subject matter expertise. Stay engaged in the system as the product's being developed for a better product. That's powerful. You'll find you'll be able to help them build a better tool if you understand a little bit better about what they're doing. Integration. Deployment. Share it with others and multiply your impact. Now, maybe it's a performance metric you're going for. You want to have huge impact. You want to get the big bonus. I get that. I had kids to put through college, and so those bonuses every year were really helpful to getting the kids through college. Or it might be altruism. You just love helping people. Regardless, it can be both. Your good work benefits many others. So, deployment. You code something up, you can share it with others. If you make some by hand workflow, it's very hard to share with others. Efficiency. Minimize the boring parts of your job. Build a suite of scripts for automation of common tasks. Spend more time doing science and engineering. Isn't it awesome? I've seen, as I teach all over our industry, that some people get very excited about that idea of being able to scrape information, combine information, do some basic analysis, build out a dashboard, automate a report. Just this automation can be very, very powerful. Always time to do it again. How many times have you done something just once? Probably. It takes about 2 to 4 times as long to script or code up your workflow. Granted, it takes more effort, but usually it's worth it. You often end up doing that same workflow 6 times, 10 times. Remember when you got the new data? Remember when you found out the interpretation was wrong, you had to rerun it? How great are you going to feel when you get that new information and you push a button and the whole thing just runs overnight? You come back the next day, you got all the reports and everything updated again. And my last statement here is going to sound a little bit arrogant, but I hope that's okay. Be like us. Coding changes you. People who are just strictly users, they feel limited by the programs that are available, limited by what other people have done. But people who can code truly harness the power of their applications and their hardware. They're able to push it into different directions. They're able to innovate in the software. What's the incremental value of machine learning? Where's this going to go? What's going to happen? Well, I think the P10 or the low side result is we'll better utilize the data to improve our decision making. With consistency, speed, we're going to avoid contradictions. We're going to do a better job of integrating everything together, understand the data. I also think we'll automate the boring, repetitive parts of our jobs. I'm not a proponent of the geoscientist or the engineer in the box. I actually don't believe that these methodologies are going to replace the scientific and the engineering aspects of our society. But I do think it's going to result in us spending more time doing more powerful science and engineering. And so I'm excited about that. I'm excited and optimistic about all of this. Focus on the immediate opportunities for the subsurface. There's so many great opportunities. One of my PhD students, Wendy Liu, just developed a really great methodology for detecting features within spatial data sets as a form of spatial data analytics. Super cool stuff. I have students working on building reservoir models using machine learning methodologies. These things are very powerful. Guided interpretation in dense data sets like seismic and smart fields, big data analytics, these are all wonderful opportunities right now to have impact in our daily jobs. We can add more value now. Optimize what we're going to do with it. Well, we're going to optimize field development decisions. If we improve what happens in subsurface development, we save money and we protect valuable resources and we protect the environment. Exploration prioritization, fast for the response of the subsurface to complicating physics, engineering, geoscience aspects. For instance, what's going to happen when you develop a field or when you go to recover groundwater or when you work in a mining setting? What's going to be the response of the subsurface to that development effort? Now, I like the idea of fast proxies. I compare it to the concept of TurboTax. Now, if you ever use TurboTax, the first thing you do is you put in a W-2, and what will happen is it'll tell you, okay, this is your estimated return for this year. It might be negative or positive. And then as you go along, entering more information, answering more of the questions, you can see that amount go down and go up and so forth in response. You understand the system. You can see how it's responding to these pieces of information. Now, I would love that for the subsurface or for any spatial complicated setting, that as you gather and add data, you can see the value of the information. You can see the impact on the response of these complicated, open, heterogeneous systems. I think that's super powerful. Let's be inspired by those working in the trades. Skilled use of machine learning. Machine learning tools are very dangerous to use as a black box. You need to understand what's under the hood. That's why I'm a proponent of starting with the basics, understanding probability and statistics when we use these methodologies. That's why I often say statistical learning, in fact, to demystify. It's a statistical method. Methods, workflows, assumptions, limitations are all very important. Scope and trade-offs between alternative methods so we can be experts using this. Now, once again, let's think about tradespeople. Now, my grandfather and my twin brother are both machinists. And my grandfather, when he passed away, he gave all of his tools to my twin brother. And I was really excited about that, to just see those tools and see them being handed down. And to see the fact that they were a toolbox full of worn machine tools. They were used for decades. In fact, the handles were worn by grandfather's hands from decades of work, perfecting his knowledge of the trade and the use of the tools. Imagine he'd have a toolbox with these tools that he perfectly understand their performance in a wide range of different settings, and he wouldn't make mistakes with them. He'd be able to do great work with these tools. Be inspired by the tradespeople. Consider their connection with their tools. That's what we should be going for ourselves while we work with these different tools. Now, remember also that while we do try to do in machine learning hyperparameter tuning, and we do try to do cross-validation of our models so we can understand their performance and optimize that in real-world settings, it's not actually possible to validate our subsurface machines. Go to the paper Oreskes and al., very, very popular paper from 1994. And if you read through it, what it tells us in summary, it's not possible to validate open Earth systems. Verification and validation of numerical models of natural systems is impossible. This is because natural systems are never closed and because model results are always non-unique. Models can be confirmed by the demonstration of agreement between observation and prediction, but confirmation is inherently partial. It's just supporting evidence. Complete confirmation is logically precluded by the fallacy of affirming the consequent and by incomplete access to natural phenomena. Models can only be evaluated in relative terms, and their predictive value is always open to question. The primary value of models is heuristic. I love that. I love this statement. It just really, really resonates with me. Remember this while you're working with your models. Your confirmation is inherently partial at best. All right. That's so awesome. And so following on from that, don't fall in love with your models or your machines. Your machines are just statistical, data-driven models. Remember the famous quote from Box, all models are wrong, but some are useful. Remember the concept of parsimony. Since all models are wrong, an economical description of the system is useful. Occam's razor. Also remember this concept right here, worrying selectively. Since all models are wrong, figure out what's most importantly wrong, and focus on that to try to improve your model. And what I would say in summary is be humble. The Earth is going to surprise you. Don't be too proud. Okay, now here's another couple of statements that I think are really useful. Data-driven approaches support traditional hypotheses-driven scientific method, that's for sure. Mazzocchi had a quote from 2015. I've shortened it here. Big data, distributed computing, sophisticated data analysis all played a crucial role in the discovery of the Higgs boson. But the discovery of the Higgs boson was not data-driven. Cool, eh? Like really, really cool. Engineering and geoscience expertise remains core. One of the professors in the department, full professor that I respect, Dr. Carlos Torres Verdin, said, don't use data analytics and machine learning as a crutch instead of learning and grasping the intuition and concepts behind the physical laws of the natural systems. Let's not become lazy. This is another tool in our toolbox, but does not replace our domain expertise. Okay, what I'm going to do now is I'm going to talk about a few unsolved problems and going forward, kind of things that inspire me. You know, this idea that some of these technologies are not ready off the shelf given our spatial context that we work with. All right, so let me talk about a few unsolved problems just to kind of further promote our humility. Issues with subsurface or in general spatial machine learning. Peaking, information double counting. This happens all the time. Some information is transmitted from the withheld data into the model. If you're really doing model validation testing, you should not be using the information in the first part to train the model. Some model decisions use all of the data. You see that? And so that's not true validation testing of the model. Also, in the Bayesian methods, I see this all the time. Information from the likelihood is included in the prior. Now, this happens all the time. A great professor at Stanford, Jeff Kers, talks a lot about just exactly what a fair prior is. It's much wider than we usually expect if we're really honest about what we know. Fair train and test split. Practitioners use the random selection methodology for train and test split. In fact, it's coded in directly as a function within scikit-learn, and I used it within my workflows too. But as I discussed in the class, if we're randomly removing 20% of the data set and we have some type of ordered data set with strings of data in space, as we often do in the subsurface, wells, drill holes, and so forth, we may be testing our model against the problem of predicting vertically half a foot. But what we really want to do with that model in reality is make predictions a kilometer or half a kilometer away from existing data. Those are two completely different problems. And so we must make sure fair train and test split means that the estimates at the test withheld data locations is just as hard as the real world use of the model, or just as easy. We might be actually too challenged with our train test split if we do some type of withheld, more of a designed method. So we got to really work that out. Multivariate spatial temporal settings. Many of the methods we're using really are truly just multivariate models. They treat the data set like it's just samples with no spatial or temporal context whatsoever. In fact, and even beyond that, many multivariate models fail to capture the full multivariate relationships. They might make some type of assumption like multi-Gaussianity or something like that. They're not capturing all of the complicated relationships, constraints, heteroscedasticity, my favorite word. Often important geoscience and engineering information may be omitted too. Often. And so these are all remaining issues. Black swans and stationarity. In spatial data analytics, we talk a lot about stationarity. That's essential for sampling and forming predictive models statistically in space and time. The model cannot be tested for data events not available in the data set. The black swan argument. Spend your whole life studying white swans. Understand everything about them, and then one day you see a black swan. You could not have predicted a black swan if you only observe white swans. This is also known as the no free lunch theorem in machine learning. Now, I think to really understand these concepts, let's go back some hundreds of years ago to a great philosopher, Hume. And what did he say about this topic? He said, even after the observation of the frequent or constant conjunction of objects, we have no reason to draw any inference concerning any object beyond those of which we have had experience. We only know what we've seen. Isn't that? I love it. I love it. It's so cool. All right. This is so awesome. Okay. So uncertainty models. Oh boy. We are challenged with regard to accuracy of our subsurface models. and a lot of what we try to do, and I commented on the issue around model validation before, is focused on accuracy. We really are focused on accuracy. But we also should be concerned with the uncertainty model coming from these machine learning methodologies. In fact, if you consider all of the uncertainties, the various uncertainties we need to integrate from the subsurface with regard to the data themselves are uncertain, there's spatial uncertainty, there's all kinds of model decision uncertainties, and we have to combine all of them together. There's a vast amount of uncertainty. And we should really be focused on validating the uncertainty model, not just the accuracy of estimates. Okay, but there's of course uncertainty in the uncertainty, and uncertainty models are truly just models and so forth. And so, in my opinion, remains somewhat unsolved. And in addition to this, we often do underestimate the uncertainty. This is a cognitive bias we often have. We believe that we know more than we actually do about many systems. All right, I'm going to conclude there. I'll record another short video where I'll talk about advanced topics, show some advanced workflows, spatial, subsurface models using data analytics and machine learning. Many of the methodologies are methods developed by my PhD students, so I thought it'd be fun to showcase what my students have been doing. I'll record that and put that in a short video. I'll stop there. This has been the concluding lecture from my course, taught for the very first time in the fall of 2019, Subsurface Machine Learning. I hope that all y'all have enjoyed the course. I hope that you have found it valuable and that you've learned something from it. If you're just tuning into this lecture for the first time, you can go back and check the entire playlist. Also check out all of the machines, the demonstrations, the workflows and examples are available to you on GitHub with the example data sets so you can actually follow the course along. Why? I believe in the idea of sharing education, supporting my students with content that's evergreen and growing even after they leave the classroom, and supporting all of the working professionals in my field. Everybody's facing this digitalization challenge, and I think the role of a professor is a role of service to support our community, our society. And so I hoped and have actually been told by many that they're using this content. In fact, a little shining star in my mind right now is the fact that there was a person who just contacted me, let me know that they lost their job, worked on some of this course content, updated some of their skill sets, and just got a job last week. And so stoked, absolutely stoked when I hear stories like that. So if you're using this content and it's helping you, let me know. It always just gets me excited and happy to hear that. All right, everybody, take care. As always, I'm Michael Perch. I'm an associate professor at the University of Texas at Austin, and I am the Geostats Guy on Twitter, GitHub, and Geostats Guy lectures on YouTube. All right, take care.